Class. In yesterday's lecture, we have understood the effective number of atoms, the coordination number, and the APF factors for the face-centered cubic and the body-centered cubic unit cell. In today's class, we will going to derive more complicated structure which in general are called hexagonal structures, and at a later stage we will see that there are two possible variants of it, and we will going to derive the coordination number, the effective number of atoms, and the APF factor for a structure which is called hexagonal closed pack structure. Now, first thing is why it is called closed pack structures. They are called closed pack structures because they have the highest possible density within the unit cell. If you remember, we derived the APF factor for FCC unit cell and it came out to be 74%. And at that time, I told that this is the highest possible density which one can achieve in a unit cell. So FCC also belongs to a closed pack structure because it also possesses the highest density. Likewise, you will see that for hexagonal closed pack structure also we will going to have the same magnitude of packing density. That will be 0.74 or you can say 74%. Now, to visualize these closed pack structures, we refer these three different diagrams which I have marked as image A, image B, and image C. What is the difference between image A, image B, and image C is the number of atomic layers making that image. In the image A, the first one, I have only one layer of an atom which is organized in a way that it makes a 1D lattice. So what you can see is vis-a-vis to its depth, there is only one atomic layer depth. And atoms are marked as B, while the valleys created between any three atoms are either marked as B or it is marked as C. Now question is why the gap, empty space between atoms are marked with two different notations, namely B and C. It is being done because if I refer the atomic layer, then I can have valley either on the top of this or on the bottom of this. So I define one of the valleys as valley B, let us call. On the top of this, we define the valleys as B, and on the other side of the same layer, we define the valleys as C. So if I focus here, you follow my cursor, then I have two possible valleys. One is on the top, let's call it C. The other one will be on the opposite side and we will going to call it B. So you understood now what is the difference between B and C? One is making a layer on the front while the another one will going to make a layer on the back of it. Now to get a better clarity, move to the image B. What we did is we take the single layer of atom A and then filled the valleys marked B with blue color atoms. So now you can see there are two atomic layers. The atomic layer A is your base layer and atomic layer B have their atomic positions which is actually occupying the valleys created by atoms of layer A. And in this two-layer diagram, what you can see is still there are valleys which is empty, that is marked as C valleys. And if you carefully look in image B, these C valleys are again the valleys which is being made by the atomic layers of B as well. If you look at the first C valley and focused on the B atoms, you can see the first C valley where my cursor is there at this point is sitting precisely in the middle of 3 atoms of B. And corresponding position in one atomic layer, which is in image A where my cursor is there, you can still see the same C valley. So now if you look at 3 atoms making that particular valley in layer A and layer B, what is the difference? The difference is in layer A, you have 3 atoms making that valley C organized in a way, it is a triangular geometry as a front triangle. While if you look the same C valley at site B, that is valley that is being in between the B atoms, you can see that valley is positioned between the 3 B atoms, which is an inverted triangle. So other way to look at the two different types of valleys is, one is in between the front triangles while the other one will be in the reverse triangle. So likewise, if I continue to keep putting different layers, then the valleys of one atomic layer is being occupied by the other. Like valleys made by A layer atom is being occupied by the B layer of atom. And likewise, the valleys made by the B layer of atom can be filled with either a C layer of atom that is shown in the 3-layer diagram, the diagram C where my cursor is there. You can see the valleys created by B atom is now being occupied by a third layer, which is C atom. Now there is also a possibility that instead of a C atom, you have the repetition of an A layer on the top of B. So you get in a 3-layer design 2 possible configurations. In first configuration, you have the A layer, on the top of that you have a B layer, and then on the top of that you have a C layer, and then it repeats. That means you have an A, B, C, A, B, C kind of geometry. This is called the CCP geometry. CCP here stands for cubic close pack structure. So what we have learned previously for an FCC is basically a 3-layer geometry. If you now look at that particular diagram, you can see the sandwich layer, that is the face centered layer, is basically your B positions of the atom. Likewise, if I arrange atoms like A layer, B layer, and then again the A layer, then I end up with another kind of close pack structure that is called HCP structure. So you got, if your atomic arrangement in 3 layers are such that the first layer and third layer atomic position is identical and the sandwich layer B occupies the valleys, then it is an ABA kind of structure which is called HCP. And if your 3-layer geometry is such that your A layer valley is filled with B and your B layer valley is filled with C, but the atomic position of C is different from A, in that case, you have an ABC kind of geometry, which is called a CCP structure. In today's class, we will going to focus on a three-layer design, which is HCP. That is, you have an atomic layer A, whose valleys are being occupied by atomic layer B, and then you have a repeat. So on the top of B, you will again have an atomic layer A. How precisely it looks like, you get a more clear idea if we look this particular diagram. First, focus on the diagram on the right hand side, where you can see one unit cell of hexagonal structure. So hexagonal structure, if you want to describe, can be described with two basal planes. You can see one base and another base on the top. Every base is being made with 6 corner atoms and one center atom that sits at the center of the okay, there is a question that if you look at the previous diagram, the B layer atom is sitting on the top and not precisely into the valley. Now, where exactly the valley is? Valley is lying between these 3 atoms of A, and if I put one more atom on the top of this, then the intervening space that is lying between these 3 atoms of A and an atom of B, that intermediate region is called valley, right? So atoms will always sit on the top of the valley. Valley is an empty space that is made by, you can say, if you arrange 3 atoms in a rectangular manner and then put the 4th atom on the top of it. So that makes you the, I let me show you this, how it goes. Please bear with the exact dimensions, because here it is difficult to make exact dimensions. So now you can see these are in plane 3 atoms, and this is the valley space. If I put one more atom on the top of this, like this, it occupies the valley is beneath this atom. So this atom is precisely on the top of the valleys, right? But what is its position? If I want to define the position of that atom, it is precisely at the center of the valley. Here center doesn't mean its vertical position. Here center means its horizontal position. I hope it is clear now. Okay, so let us continue. What I was describing was that if you have an HCP structure which is made up of 2 basal planes, each basal plane is identical, where The basal plane is made up of 6 corners, where every corner is occupied by, okay, there is another query, and I'm just allowing the participant to speak. Sahiba, now you can unmute yourself and raise your query.
सर जो लास्ट हमने देखा उसमें ए लेयर में, जैसे ए लेयर फुटबॉल्स हैं तो उनके बीच में जो स्पेसेस है उनके अंदर हम मार्बल्स डालेंगे ना स्पेसेस को कंप्लीट करने के लिए, ना कि उनके ऊपर ही फुटबॉल्स रख देंगे.
Okay, let me explain that. You are right that if I arrange like 3 balls and then there is an empty space created between the 3 balls. For example, if you look the image on the left where my cursor is there, you can see there is a valley created here, right? Every intersection of 3 atoms makes a valley on the top of which you can put one more ball. This is always be the case, right? If I take 3 balls and arrange them in a triangular manner, then it makes a small space which we call the valley. And to close that valley, the 4th atom will always go on the top of that. Now, what you can do with that valley? You can put a relatively smaller size atom into that particular valley. We will come back to filling the valleys at a later stage. Right now, what we are doing is we are simply creating the valleys. So this 4 atom geometry, where 3 atoms are coplanar and the 4th one is on the top of that, makes your valley. What I am saying that the B layer atom or the top atom sits in the valley, that doesn't mean the B atom feels that valley. It sits in the valley means its atomic position is at the valley site, right? The B atom is not sitting in the valley. So you are right when you say that the small marbles will go into that position. But that small marble is covered by another top layer which is made by the B atoms. It will be clear to you if you closely look the diagram on the left. Here we have 2 different color balls. The one that is light blue color and the another one is in red color. Now if I focus on one of the red color ball, you can see where exactly its position is. If I let me draw that part for you so it will be clear to you. If I have these 3 atomic positions and if I look below this particular ball where my cursor is there at present, that particular ball is precisely sitting in the valley of this triangular position. And similarly, if I go beneath this again, here, this particular red ball is precisely on the top of this particular valley or on the bottom of this particular valley. So the valley is not made by only 3 atoms, it is made by 4 atoms. 3 of them is in the base and the 4th one goes on the top of that. And the position of the 4th one is in the center of the valley. Horizontally, not vertically, right? Still there is some empty space between these 4 atoms and that will eventually being occupied by some tiny atoms. I hope now it is clear to you.
Yes, sir.
Right. Vaibhav, you are right. The B atoms are not filling the voids. Voids are still empty. We will going to fill them at a later stage when we will going to talk about voids. This 4-atom geometry is actually making your void. 3 basal atoms and the 4th atom on the top has some empty space in between, which we used to call the valleys or voids, right? Okay, so if you have a geometry like this, the one that is shown, the hexagonal closed pack unit cell is made up of 2 basal planes. Both are identical with 6 corner atoms and 1 atom sitting in the center. And in between these 2 basal planes, you have an intermediate plane which is marked with yellow color balls. You can precisely see there are only 3 atoms in that plane, which lies in the middle of the unit cell. That means they are completely within the unit cell. Interesting thing is to note about their positions. Now look at the position of this particular atom. Where exactly it is? It is on the top of this triangle. If I look at this particular triangle and look vertically up, this 4th atom sits. So now you see what was that B atom? The B atom is basically on the top of this particular triangular geometry. Likewise, if you refer the other atom in the B plane, it is also on the top of this particular triangle. And if I refer this third one, it goes on the top of this particular triangle. So within this B plane, where you have 6 possible triangles precisely above the A plane, only 3 of them possess an atom. And what are their position? Their position is alternate. Means you have one occupied, then another empty, occupied, empty, occupied, empty. So this geometry now you can define as, since this basal plane and the top basal plane are identical, so it is A plane, and your central plane is different from the basal one, so I define it as B plane. So if now I make a solid that is made out of this kind of unit cell, your configuration will be A basal plane, on the top of that you have B, then again there is a repetition A, on the top of that you have B, then A, and so on and so forth. So B goes in the value of A goes in the value of B, and the process continue to repeat itself. I hope now the structure is clear. Okay, so here are few things which is important. So what we have seen here in HCP, it consists of 3 layers of atoms, or you can say 3 planes of atom. The bottom layer has 6 corner atoms and 1 face centered atom in each basal plane. So if you look at the basal plane, it has 6 corners and 1 face centered atom. The middle layer has 3 full atoms. Why? Because it is not being shared with anybody else. So the contribution of the middle layer will be 100%. The upper layer has 6 corner atoms and 1 face centered atom. It is precisely same as the basal plane. Each and every corner of the atom contributes only 1/6 of its parts to the unit cell. Now this is important. What is the contribution to the unit cell by the corner? So if I go back to my hexagonal symmetry and focus on this particular position, then if I try to arrange another hexagonal structure in the empty space at the side of this atom, then I can have arrangement of one hexagon here, or I can mark that position. One goes here and the other one will go on this side. So I will have one hexagon here, another one here. Now there is no space left around this atom if I put two horizontal hexagonal unit cells around this atomic position. That means within this plane, I can have how many hexagonal unit cell? One is this, another one is here, and third one is here. And if I go now vertically up, means on the upper region of this atom, then I can have a similar 3 unit cell configuration on the top of this. Means one goes on the top of this, another one will go on the top of this, and the third one will go on the top of this. So if I now focus on this particular atom, how many unit cell this particular atom shares? It is 1, which is visible. The second one, which is marked as red line 1. The third one, which is marked as red line 3. So 3 within the plane and 3 goes on the top of that. So 6 hexagonal unit cell is being shared by this particular atom. So its contribution is 1 by 6. Is it clear? Other way to look at this 6 contribution is, if I look at the intersection to any atom, the intersection is 6, like 1, 2, 3, 4, 5th, and if I extend this is 6. So only 1/6 of the atom contributes to the unit cell. Is it clear to everyone why the contribution is only 1/6 from the corner? Because every corner is shared by 6 unit cells. Okay, so let us continue our discussion. So your corner atom contributes 1/6 to the unit cell. The number of atoms contributed by the corner atoms of both top and bottom layer is now 1/6 by each corner. And how many corners you have? 6 at the base, 6 on the top. So 6 plus 6, 12. So 1 by 6 into 12, that comes out to be 2 atoms. So corner effectively contributes 2 atoms to the unit cell. The face-centered atoms contributes half of its part to the unit cell. This is same as what you have in the cubic geometry. If you remember, this central atom, the face-centered atom, is half belonging to this unit cell and other half belongs to the top of this. So every central atom contributes only 1/2. And how many such atoms you have? 1 on the top, 1 on the bottom. So 1/2 plus 1/2 gives you total 1 atom. Since there are 2 face-centered atoms, one in the top and the other in the bottom layer, the number of atoms contributed by face-centered
So can you please repeat?
half into 2 equal to 1. Sorry?
Sir?
Yeah, go ahead.
सर जिसमें वो आपने 1/6 किया है सर, उसमें 1/6 कैसे है? एक बार दोबारा से एक्सप्लेन कर देना सर.
Okay. Suppose I am focusing on this particular atom. Can you follow my cursor? Which atom I am referring? Let me take the annotation. Can you follow my red color cursor? The atom that I am referring?
Yes sir.
Now, if I look at the sides which this particular atom makes, one side is this, another side is this. Am I right? There are 2 sides to this atom.
Yes sir.
So if I now try to arrange another hexagon, because hexagons have sharp diamond faces, I can put one hexagon which runs parallel to this. Means your one of the hexagon will go as this side common. You agree? If I
Yes, sir.
try to put one unit cell, it will arrange itself as if it is this side is common. Agree?
वो एक बार वाला
Side, on this side, one hexagon will sit as this particular face common to both of them. Can you follow that?
ये सर तो फिर तो सर दो बनेंगे ना दो
अभी
एक बार
दूसरे
वाला
पे भी
बनेगा
आ रहा
और
हूं, दूसरे पे भी आ रहा हूं. एक साइड से एक हेक्सागोन शेयर हो सकता है. यू आर राइट.
यस सर
उसी तरीके से इस साइड भी आपके पास एक फेस है इस एटम के साथ, दिस फेस. कैन यू सी द फेस विच आई एम रेफरिंग?
यस सर ये सर ये वाला नीचे लास्ट वाला ए और ए के बीच का.
हाँ हाँ, जहां पे अभी मेरा कर्सर है वो वाला फेस, ये वाला फेस, ये वाला फेस. और लेट मी ड्रॉ इट, दिस पर्टिकुलर फेस. You follow the markings?
यस सर
द रेड कलर मार्क. तो ये फेस जो है वो एक हेक्सागोन से शेयर होगा. सेम वे ये वाला फेस जो है, ये वाला, ये दूसरे हेक्सागोन से शेयर होगा. किसके रेफरेंस में मैं बात कर रहा हूं? आई एम रेफरिंग विथ रेफरेंस टू दिस पर्टिकुलर एटम. इसकी सिर्फ दो साइड्स ही हैं जो आप शेयर कर सकते हो इस एटम के साथ.
यस सर एक ये वाली हो गई वाली.
हाँ, तो एक हेक्सागोन इसके इस फेस के साथ आएगा, एक अनदर हेक्सागोन इसके साथ आएगा. सो हाउ मेनी नाउ यू हैव इन टोटल? 3 हो गए.
यस सर और एक ये वाले 4 4 और भी हैं. सही है.
अभी सिर्फ इस एटम के साथ मेरे 3 हो गए. एक तो जो हमने ड्रॉ कर रखा हुआ है, दूसरा इस साइड्स के साथ आएगा, इस पर्टिकुलर जो मैंने अभी फेस दिखाया, और तीसरा इस फेस के साथ आएगा. ठीक है, तो 3 हेक्सागॉन्स हो गए इसी प्लेन में. और इसके ऊपर मैं जाऊं, इस पर्टिकुलर एटम के ऊपर की ओर मैं जाऊं, यानी कि इस डायरेक्शन में मैं जाऊं. अगर सॉरी इस पर्टिकुलर डायरेक्शन पे अगर मैं जाऊं, इस डायरेक्शन में यानी कि वर्टिकली अप देखूं, तो एक हेक्सागॉन तो इसके ऊपर आ जाएगा, एक जो ये वाला फेस है उसके ऊपर आएगा, एक इस वाले फेस के ऊपर आएगा. तो ये एटम कितने हेक्सागॉन्स के बीच में है? 3 बेस में और 3 उसके ऊपर. टोटल ये 6 के बीच में है. आर यू गेटिंग द पॉइंट?
यस सर. लेकिन सर नीचे में सर दो नहीं है सर. नीचे में दो ही तो फेस है सर. एक ये वाला
नहीं, बेटा
ये सर साइड वाला और एक.
राइट. सी, हम सिर्फ अभी एक यूनिट सेल लेके बात कर रहे हैं, एक्सप्लेन कर रहे हैं. राइट. Solid will be made up of large number of repetition of such unit cell.
Yes sir.
अब हम क्या निकालने की कोशिश कर रहे हैं? Contribution of corner atom. तो आप कोई भी एक कॉर्नर एटम ले सकते हो, कोई भी एक कॉर्नर एटम ले सकते हो. आउट ऑफ आपके पास कॉर्नर एटम्स कितने हैं? 12. और मैं किसी एक एटम के रेफरेंस में आपको एक्सप्लेन कर रहा हूं. तो मैं कौन से वाले एटम के रेफरेंस में एक्सप्लेन कर रहा हूं आपको? मैं आपको एक्सप्लेन कर रहा हूं इस पर्टिकुलर कॉर्नर एटम के रेफरेंस में.
तो सर
जो अभी मैंने रेड कलर से मार्क किया. तो मुझे अब और कहीं नहीं देखना है. आपको लोअर बेजल प्लेन या बाकी के जो 11 कॉर्नर एटम्स हैं उसको नहीं देखना है फॉर अ टाइम बीइंग.
हाँ सर मैं भी तो ये कह रहा हूँ कि ये
दो पर्टिकुलर कॉर्नर के साथ कितने हेक्सागॉन्स टच हो सकते हैं. समझे आप?
ये सर.
तो एक तो आपको दिख ही रहा है जिसका वो पार्ट बना हुआ है. बाकी के आपको विजुलाइज करने हैं। तो एक हेक्सागोन कहाँ आएगा, जो ये वाला फेस मैंने ड्रॉ किया उसके ऊपर, दूसरा वाला ये वाला। तो इस पर्टिकुलर एटम के 3 हेक्सागोन तो इधर ही हो गए, एक जो दिख रहा है वो, और 2 जो नहीं दिख रहे हैं, बट उनका सिर्फ एक एक फेस जो मैंने रेड मार्किंग से ड्रॉ
एक तो वही है ना सर, एक तो सर बीच वाला सर यही है ना, कहते ए और ए के बीच में जो बी के जो एटम रखा है, मतलब ए की लेयर पे जो बी का, एयर के जो वाइड पे जो बी का वो रखा,
नहीं
वहां
नहीं,
पर बनाना हेक्सागोनल।
नहीं नहीं नहीं, आपने बेटा इस एटम से कहीं दूर देखना ही नहीं है। आप जो बी प्लेन में देख रहे हो, बी प्लेन तो उसी हेक्सागोन का पार्ट है, एक ही यूनिट सेल का पार्ट है। आपका एक हेक्सागोनल यूनिट सेल 3 लेयर से बना है, ए प्लेन, बी प्लेन और ए प्लेन, ठीक है। Where B plane is in the valley of A.
हाँ, तो वहां
हाँ,
पर सर एक बनेगा ना, एक बनेगा ना वहां पे सर हेक्सागोनल।
कहाँ पे?
ए बी ए, एक हेक्सागोनल बनेगा ना सर उसके बीच।
ये पूरा
मतलब जब
जो जो आपको दिख रहा है वो एक ही हेक्सागोन है बेटा।
इस
ऐसा ही मैं एक और हेक्सागोनल यूनिट सेल लाता हूं, दूसरा वाला, ठीक है।
हाँ,
और उसको ऐसे अरेंज करता हूं, अब आप देखना ये वाली पोजीशन, जिसको मैं दूसरे कलर से मार्क कर रहा हूं, से ये वाली पोजीशन, ये सॉरी, ये वाली पोजीशन, ये वाला जो फेस है इस वाले हेक्सागोन का नहीं है, दूसरे वाले हेक्सागोन का लेना है आपने। एक ऐसा ही दूसरा वाला हेक्सागोन है जिसका ये वाला फेस होगा, वो प्रिसाइजली इधर फिट हो जाएगा। देखो ये फेस और ये फेस पैरेलल है ना।
यस।
तो अगर मैं ऐसा एक और यूनिट लाऊं और उसको इसके इस साइड में रखूं, रेड के दूसरे साइड में, तो मेरे नए वाले हेक्सागोनल यूनिट सेल का ये वाला फेस इधर शेयर हो जाएगा। एम आई राइट?
यस सर। तो वो एक
ये वाला जो फेस है, जो दूसरा वाला रेड, उसके साथ भी मैं अगर एक और हेक्सागोन लगाने की कोशिश करूं तो वो मेरे इस वाले के साथ शेयर होगा, जो अभी मैं ड्रॉ कर रहा हूं। दूसरे हेक्सागोन का ये वाला जो फेस होगा,
ये इसके साथ शेड हो जाएगा,
ये इसके साथ चिपक जाएगा, राइट। तो अब इस एटम के आसपास कितने हेक्सागोन आ गए? एक तो ये जो बड़ा वाला दिख ही रहा है बना वाला, एक जो आपको दिख नहीं रहा है बट ये येलो कलर से ऐसे आगे जा रहा होगा यहाँ पे, और तीसरा जो है वो ये ब्लू कलर से मैंने जो मार्क किया वो जो इधर की ओर होगा। तो यू हैव बेसिकली 3 डिफरेंट पोजीशंस, एक तो जो इसके इस साइड आई, एक जो इसके इस साइड आई।
इस साइड आई, सही है।
तो ये एटम के आसपास 3 हेक्सागोन्स आ गए,
सही है,
ठीक है।
समझ गया सर, सही है।
और 3 इसके ऊपर की ओर होंगे, एग्जैक्टली इसके ऊपर एक, एक इसके ऊपर और एक इसके ऊपर, तो ये 6 के बीच में दबा होगा,
सही सर,
ठीक है। दैट इज व्हाई द कंट्रीब्यूशन इज 1/6। ओके, लेट अस मूव, जो हम डिस्कस कर रहे थे। So what we have is, now if I compute the total number of atoms in the unit cell, 2 atoms coming from the center of the 2 atoms coming from the corner, 1/2 each from the middle of the face, and 3 is coming from the middle plane. तो ये तो 3 हो गए जिसका फुल कंट्रीब्यूशन है, ये 6 प्लस ये 6, that makes 12, and each contributes 1/6. So 12 into 1/6 makes 2, plus ये 3 5, and 1/2 plus 1/2 each from the center. So total हो गए आपके 3 plus 2 plus 1. That makes your effective contribution of the number of atoms to be equal to 6. Since we are running out of time, we are stopping here for the time being. We will continue our discussion vis-a-vis to APF and the coordination number in the next class. Okay. If you have any doubts pertaining to our today's discussion, you can send those queries to me. I will answer them. So for a time being, I am closing our today's discussion.